First and foremost, I would like to thank Paolo Dario and Cecilia Laschi and Giulio Sandini for organizing this new edition of an important workshop, important for me, for the theme in particular, that took place 30 years ago. I doubt, frankly, that I will be able to attend the next edition in 30 years. And so I better take advantage of this wonderful opportunity that I have now. At the previous edition of the workshop, I discussed passive motion as a means to address a problem connected with the kinematic redundancy, both in artificial manipulation, robotic manipulation, and also in the control of the biological limbs, of the human limbs. Since that point, things have changed a lot. But say that the theme of redundancy, of, if you want, overabundance of information and the problems that are connected to it has remained a focus of my work, although in different contexts. And particular here, I would like to discuss how this evolved in the context of human-machine interfaces. I would say that there are two types of interfaces that I am interested in, and both have the acronym BMI. In one case, we have B standing for brain.
After being stabbed several years ago, but technology gave him hope. He was one of 4 testing BrainGate, a new technology where a chip is implanted in the brain that picks up electrical impulses. A computer then interprets those impulses as actions. The chip is implanted just beneath the patient's skull and is only a few millimeters square. Here's Matthew playing a computer game. He's not using a mouse or a joystick, rather he's thinking of where to move the paddle.
Now, I want to stop at this precise point where we talks about Matthew thinking about controlling the paddle, and I would like to use that as a point of entry for a different type of interface, where BMI, the acronym can be the same, although now we put an O, where B stands for body. And here you have another person. This is Jonathan, who is a young fellow that was suffering from a severe paralysis because following an accident. And he is doing the basically the same game that Matthew was doing, that is controlling the paddle of a Pong game. But in this case, is not controlling it just by thought, is controlling it by movement. And in particular by movement of the part of the body that remains still under his control. And this is the concept, a substantial difference between brain and body-machine interface. The concept of the body-machine interface is something that I begin developing together with Maura Casadio, starting more than 10 years ago. And the idea here is to start constructing a mapping from some high-dimensional vector of body signals to a low-dimensional control vector that could be, for example, P could be the position of a cursor on a screen, like it is in many applications of the brain-machine interface. So we have a mapping P, mapping H, where it could be a linear mapping, like it has been for a long time using principal component analysis, a principal component map. Or it could be an equivalent nonlinear form, like an autoencoder network. It can be also nonlinear. The point here is that the mechanism of construction of this map is rather simple. First, we ask a subject to engage in self-paced, spontaneous motions of whatever part of the body that they want to control, that they can control. We call that a body dance. Sometimes we also use music to facilitate it. And from the signals that are collected in this dance, we extract the two-dimensional manifold of highest variance. Through practice, what we have is that we use this manifold to present target to the subjects, and through practice, we see how subjects learn to form. So essentially, they have to form an inverse, a right inverse of H. And where in this case we have we call it G, and you have to make a presenter with a target P hat. They have to find a body motion to reach the target, and the point, the mathematical constraint is that ideally you want this G to evolve to be an inverse, a right inverse of the mapping that is supplied to the subject. Now, why the body-machine interface? Well, the brain-machine interface has been attracting a lot of attention, and rightfully so, but the body-machine interface has a specific clinical rationale. So first, it's non-invasive, is inexpensive, can be learned relatively easily by the user. But the main issue here is that this concept that you're not controlling by thinking, but by moving. So it sustains the mobility, which is extremely important, particularly for people that suffer from paralysis. I mean, there are certain forms of paralysis that are extremely rare, but also very, very severe, where no form of mobility is allowed. But in most cases, there is residual mobility, and so you want to train and use this and train this residual mobility. So it's a framework, the body-machine interface, that in many cases, unlike the brain-machine interface, can be used to combine therapy with assistance. And one thing that I want to focus here is the motor learning that takes place with dealing with this type of interface, and motor learning that leads to a new form of dexterity. So what does it mean, motor learning? Here, again, you see the image of Jonathan controlling a cursor. In this case, it's presented with a set of targets, and what you see on the right side, on the top right, you see how the performance evolved during a long, even a single session, where you start from very confused movement trajectories to trajectories that becomes more regular. So the user can also, the subject can also learn to reach the target better, but also with different trajectory. What is important through the observation of this behavior is what happens in the null space of the mapping that is given. So what we observe systematically, and I think it has been observed also in other brain interfaces, that with learning, the null space motion tends to decrease, and decrease substantially. And so what you see here, for example, you see that there are three axes. The only two, the principal components are two F2 components where the targets are presented. But so there is a third principal component which is not included in the task. And what we see is that at the beginning, the subject had some significant amount of variance outside the plane of the task, and with practice, basically learned implicitly to match the performance to the structure of the interface. That is, I thought, was one of the most significant findings. So we focused on what does it mean to learn to operate such interface, and the concept here is that you want to see what it means to learn an inverse model of the mapping. So here, schematically, you have the body signal space, you have the device space, where most of cases the device is a cursor, but the device could be also the controller of a wheelchair or a robotic manipulator, or whatever. But here you have that the characteristic of the map, because of redundancy, you have a minute-to-one mapping from body to device, and as a result, the human has to take a certain target and has to map it, has to find one solution that belongs to the set of solution compatible to this mapping. So, as we say, mathematically, we have a framework where you have Q is the configuration vector, P is the cursor, the position of the cursor, H is the mapping that we supply to the user, and through time you look at the formation of a map in G, which gives a subscript n, because the G is evolving in time. And so as it evolves in time, what we are looking at is the convergence of the product, H and G, of the combination of the forward and inverse map, the convergence to the unit transformation. Now we have developed a model for for how this process can take place by the observation of the errors. And so we start looking at the reaching error in the case of a target reaching task, and the reaching error is a quadratic function in this case, and you can construct the gradient of the reaching errors over the parameters of the inverse mapping, and by doing that you derive an expression. The expression contains also the term that was the forward map, and because of that it is implausible to assume that the learner knows a priori H, that is the forward mapping. And so what we need to do, we have to sort of modify this gradient formulation, replacing the term H, which is what we give to the subject, to a model of the map itself. So we see that we have an inverse model G, and we also want to have a forward model H. That whose learning happens concurrently to the learning of the inverse model. So in this case, we also consider a gradient descent. We have essentially the gradient descent is over the error between what the subject is observing and what is predicting, based on the estimate of the forward model. So now the H, we have an H estimated, which also depends on time, on the sequence of trials, and we can derive the gradient. So the concept actually of combining forward and inverse models is not new. It's an old concept. Was initially proposed by Jordan and Rumelart, more or less at the time, but slightly after the first workshop. And they pointed out the problems that you have in certain nonlinear mapping, where you can create a non-convex solution space for a given position of the cursor. And so because of the space of solution for a given output point is non-convex, you can derive erroneous results, because by taking the average of points that are belonging to that non-convex space. There are also other issues that may come apart, but this was one of the main rationales. So what happens is that then when you start to create this forward inverse learning, without getting too much into the detail, what happens is that the coupling of forward and inverse learning turns out to cause local minima to appear in the landscape where you perform the gradient descent. And so if you don't do anything, if you just proceeds without considering this local minima, you can get stuck on them. And it turns out that a very simple way to resolve this is to add noise in the transformation from a target to a response of the body vector. So the fact, and that's at the same time is an important thing, but it's also something that is naturally easy to obtain in a biological system, because biological systems have inherent noise, and so I think that is not necessarily a huge problem in the case of the learning of human learning of an interface. So the model validation can be carried out just by looking at how the model predicts the errors of reaching in time, and you see that this type of exponential decay of the error is well reproduced by the model of this forward inverse model learning. So I want to conclude basically with the message here is that there are interfaces that are based on brain signals and on body signals. They all contains that have the challenge of signal redundancy of and so they whole in both cases one has to deal with inverting an imposed problem. We believe that we have evidence also from other studies that learning is a process that takes place by forming internal representation of the object that has been learned. This has been seen in force fields and adaptation and in other form of learning. And here in particular, though, we see that if we think of learning through the formation of internal model, it's important to take into account the presence of random noise, which in this case has is a positive feature. It allows actually the convergence of learning. Now, one thing that I didn't approach here, but is a focus of current studies, is how these models of human learning can lead to the formation of adaptive body-machine interfaces, to adaptive interface. Adaptive interface is an interface that is somewhat mimicking or is matching the performance and the representation of the learning, so of the learner. And so one simple way to think of that is that if the learner is creating gradually an inverse model of the interface, then one may think that to facilitate learning, if you have an estimate of the inverse model of the user, you can facilitate learning by making the interface resemble the inverse of the inverse model of the user. That is such that the inverse model is a successful, has a successful outcome. And this is stated in simple term, but there are a lot of details that concern the possibility of having these things to converge. I think that concludes my presentation. Thank you for listening.